Okay, so welcome back student. In the last class, if you remember, we ended with a very important conclusion that if a matrix A, which is n by n matrix, has a set of eigenvectors phi 1, phi 2, phi n, this is a set of eigenvector of A, and corresponding lambdas are lambda 1, lambda 2, lambda n, when lambda 1, lambda 2, lambda n are the eigenvalues of corresponding eigenvectors for the matrix A, then if lambda i's are distinct, if lambda i's are distinct, then we have a relationship between these eigenvectors. What relationship we got? That their phi i's are linearly independent to each other. That means, if this is true, if they are distinct, then I can have a relationship like this and this relationship holds only when C i's or C 1 is equal to C 2 is equal to C n is equal to 0. This is the standard definition of linearly independent. So, now we will go further, with this. So, now we know that if a matrix has eigenvectors phi 1, phi 2, phi 3 with distinct eigenvalues, then these eigenvectors are linearly independent. Now, we go further, because linearly independent eigenvectors can be orthogonal to each other, and is there any special condition so that the linearly independent eigenvectors are orthogonal? Now, we try to find it out. So, now before that we need to know what is normal matrix. So, this is normal matrix. So, before that we need to find out what is normal matrix, we need to know what is normal matrix. If A dagger is equal to A dagger A, then the matrix A is said to be a normal matrix. I believe you know what is the meaning of A dagger. A dagger is a transpose followed by complex conjugate of each element, which I defined in my last class. Now, if this is the case for normal matrix, that means A dagger commute to each other. That is another thing we know from that. If a matrix is normal, then the corresponding eigenvectors of A will be orthogonal to each other. Eigenvectors of A will be orthogonal to each other. That means, if phi I and phi j, suppose these are the two eigenvectors of matrix A which are normal, then they hold this relationship, not critically this relationship, rather I should say this hold this relationship when I is not equal to j. I do not know whether it will be 1 when I equal to j or not. In that case, this matrix has to be normalized, but in general they will be orthogonal. That means, the two matrices will be perpendicular to each other if I is not equal to j. These two vectors will be perpendicular to each other when I is not equal to j. To prove that, it is a tricky proof. So, let us try to find how to prove. So, my condition is a Dagger is equal to a Dagger A. This is given. Now, I write A x is equal to say lambda x. This is a eigenvalue equation for A. Now, I can write this equation as A minus over x is equal to 0. A minus lambda I is also a matrix. I call this matrix as B. This is another matrix I call B. So, from this equation I can write here B of x is equal to 0. Now, I can show that B Dagger is equal to B Dagger B if A followed this rule. You can do that quite easily, you can check that quite easily. I am not going to do that. I assume that this hold, that the treatment is straightforward. You just make a B Dagger and then multiply B with the B Dagger, you will find some elements, and then B Dagger and B you will also find some elements. So, both the right hand side and left hand side you will find it is equal. So, now next is what I will do, that B x I know it is 0. If I make a dual conjugation of that, then it will be x B Dagger, which is equal to 0. Now, with these two equations, I also write one equation I just make these things operate over this from the left hand side and I can get these things. These things I will operate over this from the left hand side and I will get these things. Now, note that B Dagger B is equal to B Dagger. So, I am going to change that. This is still hold. If this is hold, then because these things and these things are same as I mentioned here. Next things what I will do a trick. This part I will write in a different way. This part I will write in a different way. I will write it as B Dagger x whole Dagger. This part I can write, because if you make the whole thing into Dagger, then x will convert it into this, B Dagger will convert it to B, because there is another Dagger. You know that A of Dagger, A Dagger whole Dagger is nothing but A. Using this property, I can write in this way, and the rest part is same as this. So, this is a operator over a vector, giving a vector which is daggered, and this is the same vector which is undaggered. So, daggered vector multiplied by undaggered vector, that means this is nothing but a norm of a vector which is generated by operating B Dagger over x. Now, this is equal to 0, that eventually means from that I conclude B Dagger x is equal to 0. This is my first conclusion. Now, what is B Dagger? So, I get one important thing. What is B Dagger? So, let me erase it. What is B Dagger? B dagger is, if I put B dagger here, it will be A dagger minus lambda star I. Mind it, I also make a dual conjugation of this. When I make a dual conjugation, you know that whatever the constant is here, I need to put, in principle I need to put the complex conjugate of that. I is the identity matrix. Even if I change the identity matrix to a dagger, it will not going to change anything, so it will be remain same. A dagger will be changed because I am making a dagger. So now my equation is A dagger minus lambda star I that operates over x is equal to 0, or in another way I find another important conclusion that it's x star of x. So what essentially I get, try to find out, A is a matrix, I operate over x, I find a eigen value of that, this is eigen vector. Now I want to find out what is the eigen vector or eigen value of A dagger operator when A is a normal matrix. If I do that, then you find that this is A dagger operate over x is nothing but the complex conjugate. So eigen value is nothing but the complex conjugate of the previous eigen value and with the same eigen vectors. So I will have these two equations in my hand if I write side by side. Okay. So now I will, let me write it in somewhere here because this conclusion is important. So A x is lambda x, A dagger x is lambda star x, that I got. Now let us say A x I is equal to lambda x I. I put one of the eigen vector. This is a general form. I just change and say that okay, ith eigen vector I am trying to calculate. So here for that, this is my eigen value. So I need to put a suffix for eigen value there also. So this is the eigen value corresponding to the ith eigen vector. Now I operate this with j a x I, and I will get lambda I x j x I. I get this element, this is j, this is I just operate x j and I will get something here. For this also I can say this is, I operate over jth, I have this in my hand. I will again make a dual conjugation of this. If I do, then my equation simply changed to something like this. Right. Now here one thing I should note that when I make this star will gone because A dagger x I is equal to this star is there. So the star will be here. Now I am making a dual conjugation. When I am making a dual conjugation, then this star will now remain non-star. So that means the complex conjugate, again I will make a complex conjugate of that. So this will be a non-star thing and I will have this. Now in this case I will operate for this equation with x I like this. So if I note, then these two equations these equations and these equations are same, because left hand side, this left hand side are the same thing. So, right hand side should be equal. So, if I make right hand side equal, then let me write it here, then I have x I x j x I is equal to lambda j x j x I. This equation I have. From this equation I can readily find my desired result. Now, I put these things this side. So, lambda I minus lambda j is x I x j is equal to 0. For the distinct eigenvalues, this condition holds, and the rest thing that I have is x I x j is equal to 0, which essentially means the inner product of the eigenvector of I and j, ith eigenvector and jth eigenvector is 0. That means x j are orthogonal. So, through this we can prove one very important conclusion, that if a matrix is normal, that means if I say A is equal to A Dagger, let me write once again to make it familiar. If A is commute with A Dagger, so this is a special matrix called normal matrix. In normal matrix, I will always generate a set of eigenvectors which are orthogonal to each other, which is very important, because we always want orthogonal set of vectors, because orthogonal set of vectors is a potential vector which can be used as a basis. So, these vectors, whatever the vector I get, is since it is a orthogonal to each other, I can make it orthonormal by making by dividing it with the norm of this vector, and it will be a potentially a basis. It can work as a potential basis. So, this is important. They are linearly independent, no doubt about that. On top of that, another extra information we find that they are orthogonal. So, now let us try to find some example, simple examples. Say example 1, say I put a matrix A, just check whether say 2 1 minus 1 2, this is a matrix which is given to me. Is this a normal matrix? The question is this a normal matrix? First we need to find out whether this is really a normal matrix or not. So, A Dagger will be 2 minus I 1 2 this, and now I need to find out whether they are normal or not. So, I will first find this quantity A Dagger 2 minus 1 1 2 2 minus 1 here 1 2 here. What I get? 2 into 2 4, 1 into 1 1. So, 2 plus 1 is 5, 2 into 1 1 into 2 with a negative sign. So, it will be 0, 1 into 2 2 into 1 with a negative sign. So, it will also be 0, 1 into 1 2 into 2 it is 5. So, some diagonal matrix with diagonal element 5, no problem with that. Now, I need to figure out what is the value of this when I reverse the ordering. Is this the same thing? Two 1 minus 1. So, I need to write this one here. 2 into 2 1 into 1 5 here, fine. seems to be there equal. 2 into minus 1, 1 into 2, it is 0, fine. 1 into 2, 2 into 1, 0, again fine. 2 into 1 into 1, minus 1, 2 into 2, so that means it is again 5. So these things and these things are same. So I cross verify that this is a matrix which is normal. So another example, just I change, and so this is a normal matrix. So now I will just change, say this. Is this a normal matrix? It is simple to check that this is also a normal matrix, because if I make a Dagger of that, it will be simply the same matrix I will have. If I make a Dagger of that, so it will be a same matrix 2 1 1 2, so there is no change. So that means a Dagger is nothing but a square, and a Dagger a is also a square. So no need to verify further that whether it is a normal matrix or not. Now the question is, if it is a normal matrix, then what should be the eigenvectors of this? First, second thing, this eigenvector should be orthogonal to each other. So we need to show that also, that these are orthogonals. They produce the orthogonal eigenvectors. So we need to check. So the checking is same. Last day we did few problems. So first I need to find out the characteristics or secular equation, which is this, equal to 0. So 2 minus lambda square minus 1 is equal to 0. So I find lambda minus 2 minus 1, lambda minus 2 plus 1 is equal to 0. A square plus a square minus b square formula, simple. So from here I have lambda equal to 3 one eigenvalue and lambda equal to 1 another eigenvalue. Say this is my 1 and this is my 2. These are the two eigenvalues that I derive readily. These are distinct, note that these are distinct also. Also we can cross verify that the multiplication of that I show last day, that if I add these two things 3 and 1, every time when you find out the eigenvalues, then readily you can check whether these eigenvalues are correct or not. This is a 2 by 2 matrix, simple, but if it is a 3 by 3 or 4 by 4 matrix, then you are confused with the fact that whether the eigenvalues that you are getting is the correct or not. But the simple thing is that add these two, if we add these two 3 and 1, it will be 4 and the trace of matrix will be same. So here trace of the matrix is 4, so it is correct. Also another, if we multiply these two, in this case if we multiply these two, then it will be same as the determinant. So the determinant is 2 into 2 minus 1, so determinant is 3, and if I multiply lambda 1 and lambda 2, it will be 3. Okay, so with this I can find the corresponding eigenvectors, which is the next important thing, and need to show that they are forming. So let me write it here, lambda 1 is equal to 3, lambda 2 is equal to 1, and let us find. So for lambda say equal to lambda 1 is equal to 3, I need to find out the eigenvectors. So I write it here. So 2 1 1 2 x1 x2 is my corresponding component of the eigenvectors, is equal to 3, I know the eigenvalues, then this. So from that I can have one equation, 2 x1 plus x2 is equal to 3 x1. The next equation will also be the similar kind of expression. It will not going to give any extra information. So from the first equation I can have a relationship between these two. So what is the relationship? The relationship is, if it is coming this side, So, x1 minus x2 is equal to 0 or x1 is equal to x2. Now, from that I can write another thing from this, x1 is equal to x2. So, I can make a eigenvector. I write this, my first eigenvector, say x1, not x1, say y, make a big X, whose component is x1 and x2, the eigenvectors is 1 1. I find out. This is for the eigenvalue 3. Now, I will do the same thing for eigenvalue 1, because there are 2 eigenvalues are there. So, second eigenvalue is 1. So, I need to put 1 here. If I do that, then I will find 2 x1 plus x2 is equal to x1. From this I can have a relation that x1 plus x2 is equal to 0 or x1 is equal to minus of x2. That means, my second, they are the relation, if I put x1 is equal to 1, my x2 will be minus of 1. So, my second eigenvector, which I write as a big Y, is equal to x1 x2, which is now 1 and minus 1. I write 1 and minus 1. 2 eigenvectors I get, big X and big Y. Now, I need to show that quickly. I will show that they are orthogonal to each other. So, it is simple. If I put big X, big Y, it has to be 0. So, big X is 1 1, this is 1 minus 1. So, result is 1 into 1 plus 1 into minus 1 is 0. So, with that I prove that they are orthogonal. So, with this we conclude that if a matrix is normal, then we have the additional property of that matrix, and the additional property is they produce the orthogonal eigenvectors, which is very important. They produce the orthogonal eigenvectors for the condition that the matrix has to be normal to the matrix has to be the normal. So, they will commute with their Dagger. So, with this today I would like to conclude the class. In the next class we start a very important concept, which is the diagonalization of the matrix. So, with that let us conclude. So, see you in the next class, where we find how a matrix, what is the diagonalization and how a matrix can be diagonalized with having all this knowledge whatever we have so far in our class. So, thank you and see you in the next class.